So here I'm going to continue with establishing some basic limits that we're going to then employ along with properties of limits to find the limits of more complicated functions. So today I'm going to start with the limit of n to the power 1 over n, which I expect to be 1. And to prove this, I'm going to first establish the following inequality, which is valid for all positive a and n being a natural number. This property actually follows from something called binomial theorem. The property that I used last time also follows from this theorem. Right, so last time we showed that 1 plus b to the n is bigger than 1 plus nb. So here, this is something similar, except that I extend this to the next order term. So binomial theorem tells you what the expansion of 1 plus b to the n is going to look like. It's also proved by induction, but we're not going to discuss the binomial theorem in its generality, so just two consequences from it. Okay, so because this is a chain of n infinitely many statements valid for all possible n, I can use induction. If I make n equal to 1, then the left hand side is 1 plus a to the 1, that's 1 plus a. And the right hand side, if I make n equal to 1, the quadratic term disappears because 1 minus 1 is 0. And then you have 1 plus a plus 1, so again, this is 1 plus a, so base step works. So next we do the inductive step. We assume that for n, the statement is true, and I want to prove the same statement but for n plus 1, using what I know about the step n. So 1 plus a to the n plus 1 is 1 plus a to the n times another 1 plus a. Use inequality and the fact that 1 plus a is positive, use the nth step and the fact that 1 plus a is positive to get this. Then expand, multiply out by 1 plus a, and then collect similar terms. So with a squared I have this and that. So this is with a squared. With a I have this and that. So this term. 1 is still 1, and then there is one extra piece, which is 1/2 n times n minus 1 a cubed. All right, so then now I can combine things. Actually, I don't need to combine anything for 1 because 1 is just there by itself. Na plus a, I can factor out a to get n plus 1a. And then for these two guys, there is a common factor of na squared. So what is left then is 1/2 of n minus 1 plus 1 once I factor out na squared. And you can easily convince yourself that 1/2 times n minus 1 plus 1, that's actually 1/2 n plus 1. So we end up with this, plus the term with a cubed, which is the only term with a cubed. And this term with a cubed actually is positive because I assume that a is positive. So if I drop it, I have this inequality. And then if I examine it, I get exactly what I was looking for, right? Because this is the same statement as what I see here, except that n should be replaced by n plus 1, and it is. N should be replaced by n plus 1, and it is. And n minus 1 should be n plus 1 minus 1, n. And that's what I got here. So that means that indeed the n plus 1 step holds, and so I proved this inequality for all n. And I'm going to use it in trying to prove the fact 3 that the limit of n to the power 1 over n is equal to 1. So to do this, I'm going to consider the sequence Sn equal to n to the power 1 over n minus 1. Okay, so then if that is the case, I can solve this for n. So n to the power 1 over n should be Sn plus 1. And therefore, taking nth power of both sides, n to the power 1 over n to the power n, that's n. This should be equal to Sn plus 1 to the power n. And by the fact that we just established, this is greater or equal than 1/2 n times n minus 1 times, so my a now is Sn, so times Sn squared plus n Sn plus 1. Now, Sn actually is clearly positive because if I'm taking a number n which is greater than 1, right, when n is greater than 1, and that number is raised to the power 1 over n, if I take a root of a number which is greater than 1, I'm never going to get anything that is smaller than 1. So therefore, in fact, we can put here that this is always greater or equal than 0. And now if Sn is always greater or equal than 0, then the sum of these two guys is always greater than 0, right? Because I have something which is greater or equal than 0, Sn, times a positive number plus 1, so this has to be greater than 1, so automatically this guy is greater than 0. And so what we get is this, that if I ignore NSN plus 1, I'm going to get something which is strictly smaller than this. So this is going to be greater than 1/2 n minus 1 times Sn squared. So ignoring then the middle parts of these chain of inequalities, what I get is that n must be greater than 1/2 n minus 1 times Sn squared. And if I solve this inequality for Sn, so first I would need to cancel n, right? So it follows that 1 is greater than 1/2 n minus 1 times Sn squared, and therefore 2 over n minus 1 is greater than Sn squared, right? Because I multiply both sides by 2 of both sides of this inequality. Multiply them by 2, divide by n minus 1. And then if I take a square root of both sides, the inequality should still be preserved because square root is an increasing function. And so it follows that Sn must be less than the square root of 2 over n minus 1. And by using the definition of a limit, I'm not going to do that here, but using the definition of a limit, I can prove that this, actually let's do use the definition of a limit and prove this. So now choose any epsilon greater than 0, and what I want this quantity Sn minus 0 be less than epsilon, right? Because if I want n to the power 1 over n to go to 1, then I would expect that n to the 1 over n minus 1, that should go to 0, right? Again, I'm trying to establish that the limit of n to the power 1 over n is equal to 1. So if I look at n to the 1 over n minus 1, I expect that this quantity would go to 0. So I want to show, in fact, let's maybe write this here. So we want to show that the limit n goes to infinity of Sn is going to be equal to 0. And so to this end, let's choose epsilon greater than 0. And so let's see what we want. I want Sn minus 0 to be less than epsilon if n is bigger than capital N, right? For some capital N. In R. So the only thing that I need to do is I need to select, figure out how to select capital N. Okay, so let's see. We have absolute value of Sn minus 0. What's that? That's absolute value of Sn, but Sn is positive, so this is Sn. And I know that Sn is less than the radical of 2 over n minus 1, right? I know that from here. And if Sn is less than the radical 2 over n minus 1, I can try to make that guy less than epsilon. And doing this is equivalent to saying that 2 over n minus 1 I want to have to be less than epsilon squared, and I can solve this for n. So this is equivalent to saying that n minus 1 should be greater than 2 over epsilon squared. And that's the same thing as saying I want n to be bigger than 2 over epsilon squared plus 1. And I'm going to call that capital N. And so then, if n is bigger than capital N, I can follow the chain of the inequalities that I've written here backwards, right, to see that Sn minus 0 is less than epsilon. So, following inequalities backward, retracing it, it follows, or we conclude, that Sn minus 0 is less than epsilon, and so therefore limit n goes to infinity of Sn is equal to 0 by definition of the limit. Okay, so if then that is the case, what is Sn? Sn was defined as n to the power 1 over n minus 1, right? So then what we conclude, then the limit n goes to infinity of n to the power 1 over n. That should be the same thing as the limit and goes to infinity, n to the 1 over n minus 1 plus 1, right? I'm simply adding and subtracting 1. And then this quantity is Sn, right? And then by properties of limits, limit of a sum of two sequences, right? That should be equal to the limit of the sum of two sequences must be the sum of two limits of those sequences. So this should be the same as a limit n goes to infinity of Sn plus a limit n goes to infinity of 1. Limit of a constant is that constant. Limit of Sn is 0. So 0 plus 1, 1. And that's what we set out to show, right? That the limit of n to the power 1 over n is equal to 1. All right, so number 4. If I take a limit n goes to infinity of a to the power over n, then the claim is that this limit is also equal to 1. As long as a is equal to 0, is greater than 0, because otherwise you will not be able to take roots of a. So this is true for any a greater than 0. All right, let's prove this. Proof. Let's consider the case consider the case a is greater or equal than 1 first. So then, what do we have? So then if n is greater than a, it follows that a to the power 1 over n should be less than n to the power 1 over n. Again, nth root is always an increasing function. So if I replace a by n when n is greater than a, then I would expect that the same inequality would be preserved for nth roots. And also, because a is greater than 1, then number greater than 1 raised to the power 1 over n should still be greater than 1. Okay? All right, so then the limit n goes to infinity of a to the power 1 over n, if this limit exists, then it cannot be less than 1, right? So this limit must be greater or equal to 1. And because the limit n goes to infinity of n to the power 1 over n, this is equal to 1, this would imply that the limit n goes to infinity of a to the power 1 over n also should be less or equal than 1. Right? Because a to the power 1 over n is always less than n to the power 1 over n for large n. And so then a limit of this quantity cannot be greater than 1. So it must be less or equal than 1. And then because the limit of a to the power 1 over n is greater or equal than 1 in here, and is less or equal than 1 in there, the only choice is that the only possible choice when both of these inequalities hold true is that the limit is actually equal to 1. So limit n goes to infinity, a to the power 1 over n is equal to 1. So that is as long as a is going to be larger than 1. So now, suppose a is less than 1. But if a is less than 1, then 1 over a is greater than 1. And if 1 over a is greater than 1, then of course, from a part 1, we know that the limit n goes to infinity of 1 over a to the power n must be equal to 1 by what we have just showed, right? If a is greater than 1, then the limit is of a to the power 1 over n is equal to 1. So 1 over a is greater than 1, then the limit of 1 over a to the power 1 over n is equal to 1 by the first part. Okay, but then what is the limit n goes to infinity of 1 over a to the power 1 over n? I can always write 1 over a to the power as top to the power divided by the bottom to the power, 1 to 1 over n over a to the power 1 over n. 1 to any power is 1, so this is the same thing as a limit n goes to infinity of 1 over a to the power 1 over n. Okay, but then that limit I know is equal to 1. And I also know that the ratio of two limits, limit of the ratio of two sequences is the ratio of two limits per what we discussed above, as long as the sequence in the denominator and its limit are not equal to 0, which they're not in this case. So this is the same thing as a limit n goes to infinity of 1 divided by the limit n goes to infinity a to the power 1 over n. Limit of 1 is 1. This is the thing I'm looking for. And I know that the limit that I started with is equal to 1. So let me actually stick it in here. And so by solving the equation 1 is equal to 1 over limit of a to the power 1 of to the power 1 over n, that gives me that the limit n goes to infinity a to the power 1 over n, when a is less than 1, that this is also equal to 1. And so we're done. So I'll continue in the next lecture with more properties.